So now that we've talked a bit about the structure and the functionality and a little bit about the performance of this app, let's visualize how it works. And this will give you yet another perspective on how things behave. There's actually another variant of this program, which you're welcome to take a look at, called the ImageStreamGang application. And this actually uses a whole different framework available with pre-Java 8 capabilities. It actually uses Java 5 capabilities called the executor service and the executor completion service. And those are cool, but not as cool as the Java 8 related stuff because they don't combine the functional programming features because Java 5 didn't have functional programming at that point. But it is kind of fun to compare and contrast the two approaches. So this app uses an interesting parallel stream, and it combines the object-oriented functional programming features. What it does is it'll give a list of URLs. It'll go and ignore the ones that are already downloaded and processed. So if they're cached, it ignores them. It'll download the non-cached images in parallel. It'll apply a list of filters to each image in parallel. It'll store the filtered images in the file system in parallel. And then after everything's been downloaded, at that point, the images can be displayed to the user. And that's actually pretty cool too, because it uses a couple of different activities, which are Android user-facing capabilities. So there's one activity that's used to download everything, and once everything's downloaded, another activity pops up, and you can use it to actually browse the images that you've downloaded. So it's kind of like the gallery app, a little bit like the gallery app. And one of the things that's really neat about this is the pipeline we wrote to do this in parallel closely aligns with the description of the features or the functionality of the app. So that's what's called domain intent. So if you take a look at the description here, ignore cached images, download non-cached images, apply filters to each image, store the filters in the file system. Those things are pretty much one-to-one from the human-readable description on the left, on your left, and then the pipeline of processing on the right. And so that comes back to this point I've made a number of times about how streams helps to elevate the programming abstraction level so that the domain intent, this stuff over here, matches pretty much one-to-one to the computations that are expressed. And that's really helpful in my mind, because otherwise you get lost in all the details of looping and branching and all this low-level gobbledygook. So in a nutshell, it helps to close the gap between the design intent and the computations that implement the design intent. So here's kind of what this looks like. So now we're moving away from high-level description to visualization of what happens. So a user gives a list of image URLs, and then in parallel, we're going to convert that list of URLs, that collection of URLs, into a parallel stream of URLs. And undoubtedly, you remember that the way the stream splitterator works is that each element in that array list will have its own task that will be given to the fork join pool to run in parallel. So each of those things will then run in one thread of, it'll run in a thread, and all the computations we're about to see are going to take place in that thread, in the pool. So the parallel stream will create a stream of image URLs. We're then going to input that into the next intermediate operation in the pipeline, which is going to be the filter operation. And what filter is going to do is it's going to ignore cached images. So what it's going to do is it's going to not let anything through that's already cached. So if it's cached, then it'll be ignored because we're filtering for not cached. So it'll only let non-cached things through. That's what that's trying to say. We will then have a stream of non-cached image URLs, and then that non-cached stream of image URLs will be passed as input into the map method, and the map method will then download the non-cached images in parallel. So each of these images, each of these URLs will then be downloaded in parallel using something called blocking download. And remember blocking download when we talk about completable futures later. The parallel streams model is inherently synchronous. So you can block. And you can block because you've got separate threads, which of course are using your fork join pool to run in parallel. And so we can do blocking downloads. So it's a blocking download. We then end up with a stream of downloaded images. Now at this point, we've gone from what we had before, which were URLs. Notice how we had URLs, list of URLs, stream of URLs, and so on. And now we've done map, and now we have a stream of images. We have a stream of downloaded images. And so that stream of downloaded image objects is then going to be fed into the flat map intermediate operation. And remember that the main difference between map and flat map is that map always gets back the same number of elements that it gets in, unless an exception is thrown, but that doesn't happen here, let's assume. In contrast, flat map can give back more, less, or the same number of elements. In this particular case, what flat map is going to do is it's going to apply multiple image filters or image transforms to each downloaded image, each non-cached downloaded image. And so we're going to end up with more images coming out than we came in with, because we're going to have, let's say for every image, we're going to apply 2 or 3 transforms to it. So we'll have a lot more elements in the stream coming out than we did coming in. So that's why we have to use flat map. So you end up with a larger number of images. So apply filters will apply the filter to each image in parallel and store the filtered images in the file system. We then have a stream of filtered and stored images. That's what's coming out of this thing. So the images that are coming out have been filtered and stored. We collect all these things into a list. And that, of course, is where all the processing actually takes place, right? So within each of these threads, when collect is hit, it then goes and it will pull the elements through using the split iterator to pull the elements through each of these intermediate operations, and then it will accumulate them into, in this case, a non-concurrent collector. And when we're all done, we'll have a list of processed and stored images. So that's what we end up when we're all done. So filtered and stored images are stored in the list. And at that point, we can then go ahead and display them. So the cool thing about this is that the Java Streams framework orchestrates all of these steps to run in parallel. So we don't really have to think a whole lot about this. In this particular program, trying to think, I don't think we don't actually have to use any synchronizers in our code at all. The only place where synchronizers would even be necessary would be at the file system level, where files are being created and written read and written to, and all that's synchronized by the underlying Java file system methods and implementations. So the Streams framework orchestrates all the parallel computing. You don't have to think much about any of the computations. You just write them the way that it does the decomposition into separate pieces, giving it to the fork join pool, using split iterators, using collectors. All of that is magically hidden from you, which is great. So that was a quick visualization of what this program looks like when you run it.